My dear students, good morning. Today we will study Unit 1B, Unsteady Flow. In the last year, in second year, FM1, we have already studied what is steady flow. Steady flow is nothing but it is a flow in which the flow characteristics such as velocity, density, pressure at any point do not change with respect to time. Whereas unsteady flow, on the other hand, these characteristics will change at any point with respect to time. That is the difference between steady and unsteady. You are aware of it. So far, major problems which you have seen in FM1 is with respect to steady flow. However, few problems of unsteady flow are also of more importance from engineering point of view, because the unsteady flow, in case of this, forces due to variation are also involved with respect to velocity and momentum, because of which the problems associated are little bit more difficult to solve. Now we will see the different types of unsteady flow. Unsteady flow may be classified based on the manner in which a particular variable varies. There are 4 cases. We will see one by one. First case, flows in which the variation of variable is rapid and random. Rapid and random. Here you can see rapid and random. Good example of this is a turbulent flow, because the characteristics will change very fast and abruptly in general. Similar case, the examples may be turbines and problem associated with high head gates. The second one is flows in which the variations of velocity are periodic, either slow or rapid. The changes are slow. If the changes are slow, such problems you have studied in FM1, whereas in problem like surge tanks, water hammer in pipes, etc., where the velocity changes very rapidly, therefore we may require to consider the elastic forces also into account. Now we shall come to the third case. In third case, the flows in which a variation is non-periodic but slow. For example, in case of flow through openings under variable head and flood routing, this problem arises. We can solve that, and that is included in the syllabus. Just will come after this class. Lastly, fourth case, flows in which the flow is caused due to motion of the body at constant velocity. This is to be kept in mind. At constant velocity, the flows in which the flow is caused due to the motion of the body. Flows which are due to translation of surges and waves are good examples of this category. However, these problems can be transformed into steady flow problems just by using the concept of relative motion. So there are 4 cases. Now the third case, as we already mentioned, the flow is non-periodic but slow, that comes under flow through openings under varying head. The various devices such as orifices, mouthpieces, and pipes are used in order to let off the water from tank or a vessel. Suppose we consider any shape of the vessel to start with, because we are required to arrive the time of emptying the tank, general formula for which we consider any shape as shown in figure here. Let us consider. Let H1 be the head above the device. This is the device, orifice or mouthpiece, whatever it may be. H1 is the head above the device from which the head is to be reduced to H2. What is the time required is to be found out. Now let H be the head at any instant and let it fall by small amount dH in small interval of time dt. Let us assume. Now, if I assume A is the area in plan at this stage, capital A is the area of liquid surface in plan, then volume of liquid which is moving through orifice is equal to A multiplied by dH, and the total water which is discharged through the orifice, if we know small a as the area of the orifice and CD as the coefficient of discharge, then amount of water which is let off through this orifice may be equal to Q into dt, because we have to consider here also the time dt. Therefore, we can equate these: volume of liquid leaving the tank must be equal to discharge through the orifice. That will become equal to minus A into dH must be equal to Q into dt. Therefore, dt is equal to minus A by Q into dH. This minus sign indicates as time increases or as water flows through the orifice, H reduces above the device. That is the reason why it is affixed with minus sign. Now, therefore, the total time can be found out by integrating 0 to t dt, that is equal to H1 to H2 integral minus A by Q into dH. Here there are two cases. This is the general formula. Suppose if I am considering rectangular tank or cylindrical tank, wherein from top up to the bottom the dimension is same. That means area of liquid surface will remain same. That is, A is constant. Then in the above equation, express Q in terms of H and integrate. Suppose if A is variable, then express both A and Q in terms of H, and then we have to integrate. Because, for example, if you consider a hemispherical tank like this, then this area of liquid surface from top up to the bottom is not constant. It is gradually decreasing. As the water let off, the area of liquid surface also keep on reducing. That is the reason why we have to express both A and Q in terms of H. Now we will see for when A is constant, time of emptying a cylindrical tank. So look here. Look at this figure. This is a cylindrical tank. Let H1 be the initial head and it is to be reduced to H2. Let H be the head as it is assumed above. H is the head above the device. At any instant, let it fall by dH in time dt seconds. Then we can make use of general formula to find out the time of emptying the tank. Capital T is equal to integral 0 to t dt is equal to H1 integral H1 to H2 minus A by Q dH, where A is constant. Now we can substitute the value of Q in terms of small a and CD and height H above the device. That's why capital T is equal to H1 to H2 integral minus A upon CDA root 2 GH dH. That is equal to so on. So if you simplify, you will get after integral minus A CDA root 2G whole multiplied by 2H to the power of half H1 to H2. Now we can write down T is equal to minus 2a CdA root 2g. Substitute the value H2 and H1, root H2 minus root H1. Suppose if we interchange this H1 and H2, then this minus sign can be removed. Therefore, T is equal to 2 capital A divided by CD small a multiplied by root 2g whole multiplied by root H1 minus root H2. This is the expression for time required for emptying the cylindrical tank. That means when A is constant. Suppose in the same derivation, if this is asked, if the tank is to be completely emptied, then what is the value for H2? H2 will be equal to 0 because it is completely to be emptied. Therefore, T will become very simple, 2a divided by CD into small a multiplied by root 2g multiplied by root H1. Now let us take case 2. Let us take case 2 when A is variable. When A is variable. For that, we shall consider hemispherical tank. In the similar way, all assumptions. So that's why you look at the figure where R is the radius of the hemispherical tank. H1, H2, H, DH, etc. are same as above. You can refer it. Now our question is, since area of liquid surface in the hemispherical tank keeps on decreasing, we have to find out this AB as the radius while calculating the area. To calculate that, we have to construct a right angle triangle OAB. Then AB squared is equal to OA squared minus OB squared. Am I right? Am I right? Here, OA squared is equal to OB squared plus AB squared. Therefore, AB squared is equal to OA squared minus OB squared. That is equal to R squared minus of R minus H whole squared. If you simplify, you will get AB squared is equal to 2RH minus H squared. Therefore, the area of liquid surface will be equal to A is equal to pi multiplied by AB squared. That will be equal to pi multiplied by 2RH minus H squared. Now, using the general equation, T is equal to integral 0 to T dt, that is equal to H1 to H2 minus A upon Q multiplied by dH. Substitute the value of A minus pi 2RH minus H squared divided by Q value CdA root 2GH. Now, next step is just we have to take out the constant outside the integral. Then T is equal to the constant value minus pi CdA root 2G integral H1 to H2 2R h to the power of half minus h to the power of 3 by 2 multiplied by dH. After you integrate, you will get it. Now, here also, in order to remove this minus sign, just we are taking, instead of H2 minus H1, we are taking H1 minus H2. If you simplify, you will get the time required to empty the hemispherical tank from H1 to H2. T is equal to 2 pi divided by CdA root 2G whole multiplied by 2 by 3 or H1 to the power of 3 by 2 minus H2 to the power of 3 by 2 minus 1 by 5 minus 1 by 5 H1 to the power of 5 by 2 minus H2 to the power of 5 by 2. Suppose in the same derivation, furthermore is asked by increasing 1 or 2 marks. Tank is full initially, H1 is equal to R, and if it is to be completely emptied, then H2 is equal to 0. Just you have to substitute the value of H1 is equal to R and H2 is equal to 0. So H1 is equal to R radius and H2 is equal to 0. You have to substitute in the equation to get the expression. T is equal to 14 by 15, 14 upon 15 pi r to the power of 5 by 2 divided by CdA root 2G. Okay, this completes that. Next, in the next class, we will go for compressibility of fluid, celerity of fluid or sound wave, then finding out the expression for celerity of pressure wave, both for rigid case and elastic pipe is used, and then lastly water hammer. Okay, thank you.